I know, yeah, that's going to be ranking. Probably join the list of 30 or more inches.
The worst you can hope for is a mediocre.
Right. Well, I think if we don't get an average mark of 7.1 inches, we're below an average mark. We won't get older than that. So we have a little bit of leeway, but probably not much.
Whenever you're ready, Jim.
Okay, I guess let's get started. Okay, welcome to our weekly weather discussion. Special welcome to our visiting potential graduate students. It's a real pleasure to have you here today. I hope you have a good visit and that you learn enough about the department that you can leave feeling like you learned more than you had known before. It's a great place to work and a great place to study. I hope you get especially a chance to talk to some of our current graduate students. They'll give you the real skinny. You know, all the rest of us will be on best behavior, but they'll tell you what's really right about this place. And I'm confident they'll say nice things. I'm Professor John Martin. This is Pete Pokrant. He's our tech guy and all-around valuable individual. Professor Tripley's here in the front. Christy Bellinson is in the back. So if you want to talk to any of us after the discussion, we encourage you to do that. And Professor Rao just walked in as well. So maybe some of you have already met her and some haven't. So. Okay, I want to start with a few things about the wrap-up of the meteorological winter, and I'll do them on my own machine here. So, for a number of years now, motivated by a particularly boring winter, this one fits the bill as well, in 2011 and 12, I started keeping track of the aerial extent of the -5 air at 850 millibars. And I do that over the whole northern hemisphere during the winter time, December 1st to February 28th. No leap days. And this is this year's daily time series. So let me explain what's on this graph. The solid blue line is I think about a 66-year average up through about 2014 from the NCEP reanalysis data. For each calendar day, the long-term average of 66 years of like February 20th is right around there, 69 million square kilometers of cold air, colder than -5 at 850. And then that's surrounded by plus and -1 standard deviation for each day. And then the blue lines are the maximum and minimum for that day. So it gives you the sense of the range. And then the red line is this year's, December 1st, 2021, February 28th, 2022, this year's daily time series. And so this turns out to be the 17th warmest winter in the last 74 by this measure. And the way that I figured that out is to just add up all the departures from average, this being a -1, this being a +1. Do it for all through 90 days. You can rank all the winters that way. Quinn.
What do you do about leap years at February 29?
I don't count them.
Okay.
Yeah.
I've had a similar problem.
Yeah, so there's,
I couldn't figure out what to do.
and that has cost me 18 days so far, going back to January 1st, 1948. So that's not really that much, but yeah, I drop them out.
Okay.
And I stole that idea from people in literature. Most people in the climate literature, which I'm not part of really, they don't deal with leap days. It's a weird thing. So I don't deal with it. But I add up all the departures, and that's just a simple way to rank every year. And this turns out to be the 17th warmest, the 17th largest negative anomaly of all of the 74 years. So that's really middling. I mean, I guess I don't mind. We're only 20 years into the century, and 15 of the warmest 20 have been in this century. So we all know what's going on. There's no doubt about it. The planet's warming up, and this shows that's true at 850 millibars, as well as it is apparently at the surface. So it's kind of neat. Now, one thing I was thinking about, I want to show you the next graph. If we could, oh, Pete, no, Pete, I'll do it, like we said. I'm sorry, I forgot it. This is 5 different thresholds, -5s right here, 10 all the way to -25. 3 different data sets. The red lines are NCEP reanalysis and or GFS, 1 degree by 1 degree data the last several years. And then the green is the climate system forecast reanalysis, and the blue is the, I think, ERA 40 or something. This is kind of an older chart, but I now have JRI 55 and ERA 5 data as well. And they look the same, I just didn't have a chance to prepare them for you. But you can see there's a systematic trend downward. These trend lines are about 4.5% shrinkage in the last 70 years, and it's at the 99.9% significant level. It's true at all of these. On a figure that I had in the paper in 2014 when I first did this analysis, you can also see the Arctic February sea ice extent is exactly parallel to the tendency of the minus 20 at 850. So it's exactly the same signal. So things are warming up. But there's a lot of interannual variability. And there's quite a number of mysteries that still remain for me about what's going on here. For instance, 2016, there is a low point in the last 10 or so years, but it's a really substantial low point at the colder threshold. So it was harder to make cold air, really cold air at 850 in those years, and not quite as difficult. It had parallels in the prior past at minus 5. So that's kind of interesting to me. I don't know if that is another year like that right here, which is like 1995, I think, or something. What was I going to say besides? Oh, yeah, if you count along, I don't think there's a single point in the time series where 3 straight years go in the same direction. Zoe.
Have you tried filtering it by different teleconnections to see the influence of ENSO?
In the paper, I had to do it by ENSO, but because that was a reviewer comment, which was a good comment. It turns out it doesn't really have an impact. Neither does snow cover variation. And that's probably because the hemisphere is bigger than the land area. But I haven't done any more systematically on questions like that, which would be kind of interesting.
I don't think it influences necessarily the trend, but just be interesting to see if that's how you can pick out some of those extremes.
Yeah.
deviate.
Yeah, that could well be. So that's something that I could do next on this. But there's never more than 3 years in a row in the same direction, which is kind of interesting to me.
So it looks like maybe the dominant mode is a biannual.
I don't know. This is the time series that you could do a Fourier analysis on. You can figure that out maybe. I haven't done that. So I just wanted to show you the streak continues. Prior data I think I'd shown before only went up to 2016, and the trend is exactly the same when you add the extra 7 or 6 years. Okay, let's go to the next thing, which is just a reminder of this year. And it occurred to me, thinking about the situation in Ukraine and how it might impact markets around the world, that one of the words they use in market research all the time is volatility. And it strikes me that volatility is just how much up and down do you get, right? I mean, that's what you and I started to look into that. And really the basic measure of it is the standard deviation of departures from average, or 0, whatever you said is your 0 line. So I can do that with this data set. I can say, for every one of the 74 years I now have, this average is portrayed on the curve because I keep a standard value on the left-hand side, but it could just as well be a straight line, and then you just figure out what the standard deviation of the departures is. And large standard deviations would be years with a lot of volatility in the 850 millibar cold pool. Years with substantially less standard deviation would of course be less volatile years. Well, look at this. This is hot off the press from yesterday. These are the 4 most volatile years. Maybe it's ugly. The background's the same as what you just saw on the prior diagram. Here are the years themselves, color-coded. But one thing that jumps out is gigantic excursions that take, large chunks of the whole season, buildups of cold air, decays of cold air that take a whole month. These are characteristic of these volatile years. So the amplitude is not separate, apparently, from the length of time it takes to build them up. That seems interesting to me. And here are the least volatile years, where one sees immediately, by eye anyway, the frequency of ups and downs is a lot higher and the amplitude is smaller. And so it strikes me that maybe there's something interesting about comparing these winters to these winters. For circulation differences around the hemisphere. Remember, it's a hemispheric measure. Various other things. And so I'm pursuing that right now. It may well be a blind alley, but it doesn't take that much time. And it's really interesting to me. So you never know what you might find if you just scour around and search through data sets. Because this does seem to be something here. And I'm talking to Michael Morgan the other day. One could also do a Fourier power spectrum on these years and see, does the hemisphere pulse differently in these highly volatile years than it does in these? It looks like the answer is obviously yes, but why? Is there anything that kind of systematically forces that? I don't know yet. Caleb.
Have you looked at the strength of the polar vortex in the volatile and non-volatile?
This is right from yesterday, so no, great questions. What are you doing when you're done with your undergrad, Caleb? So it's something to think about. I mean, really, this is something we could have fun investigating because there might well be some of those connections. I don't know. And then, Zoe, your comment about other teleconnections, like with ENSO, maybe some other things like that, I haven't put these to the test either on that. That might be something of interest. So, and jet waviness. I did do that, but not with just these 4 years. Subtropical jet waviness has little to or nothing to do with the extent of the cold air, but the polar jet waviness has a little more to do with it, at least by a regression line, so far. Okay, so that's all I wanted to show you on this. And then let's get back to our regular stuff. Okay, so let's start with the satellite movie, Pete, over the continental U.S. Great, so here's our infrared. I think it's the last 6 hours or so. We've got a developing weather system here in the Intermountain West, Four Corners region. That's going to have a major role to play in our weekend weather. It will not only change the temperature of the region substantially, but we may hear our first rumbles of thunder. In fact, actually more than one rumble of thunder probably by the time the weekend's over. For the first time in a very long time. I don't even know the last time it substantially precipitated here, let alone thunder and
You know,
lightning.
we've had thunder actually in one of those snow events this past couple.
And I heard that one. That's the last time I actually heard it. But when's the last time it happened more than once?
Oh,
I think that was the only, it was a stray
yeah,
thunderclap.
yeah.
At least it was where I was. I don't know if you heard more.
No, I only heard one.
But you're right. That is one recent event, but that is the last one that I can even recall. So it's been exceptionally boring. So hopefully that's going to change this weekend. We'll talk a little bit about the evolution of that forecast when we get to the forecast part. I love making the point about the infrared satellite movie at this time of year because you can see how fast it warms up in clear sky locations, especially to the south. It didn't really do so in Boston. Look at this. No warm up there at all in these 6 hours. The whole southeastern U.S. warmed up. The entire country of Mexico warmed up, and a large part of the isthmus did as well. And you can see that nicely in the infrared. Very cold air streaming off the continent here is evident also in the cloud streaks that come off of maritime Canada and the Gulf of Maine. That's all in the wake of a series of cyclones. One of the more important, impressive ones now in the northern Labrador Sea, and a secondary one farther to the south, heading up into that region.
Richard, can I also mention that people are starting to get off the lakes in Madison, even though it's still
is that right?
averaging below freezing.
Yeah.
The lakes start to melt because the sun angle gets high and it melts underneath.
Yeah, that's really bad news if you're out at the wrong time. Yeah, the sun
Yeah.
angle is a killer. We were talking about the threat of, and you'll see in the forecast, there's the threat of some snow next Friday, but that's the 11th of March. And snow at that time of year is really hard to keep on the ground for any length of time. It becomes much less of a nuisance, and it's exactly the same thing. It's a function of the sun angle. In fact, my neighbor and I, when we've gotten March snows in the past, especially if it's a Friday or Saturday, we'll just go out and shovel a few spots on the driveway and let the albedo difference do the rest of the shoveling, because it works in March. So it's really nice. You can even see some shear, which is really kind of cool here. Here come the northwesterly winds, a little bit less northerly by the time you get to these low stratus clouds, but the high cirrus above are coming straight from the west. So that is clearly a backing with heightened cold air advection, and that's consistent with it being behind the cold front. So that's kind of nice. Sometimes you can see the thermal wind in the satellite movie, and you can in this case, especially here. I mean, look at this. See these elements moving southeastward and these moving straight northeastward, so there's strong cold advection going on there in the geostrophic wind field.
You also see the roll vortices underneath from the cold air overriding the water, on the water surface.
Oh, yeah.
You're getting low vortices instability.
Yeah. So it's really nice. There's a lot to see on the satellite picture today in the Atlantic. So let's see what's going on off the west coast, just to set the stage. There'll be more to say about this storm, of course. So the west coast has a couple of really nice little disturbances close in to the continent. One of them is down here just south of the Bight. You can see it kind of coming on shore, and we'll see in the radar summary that band has a curvature to it and a rotation to it as it comes on shore, north of San Diego. That's a nice little cold upper vortex coming in that part of the state. Then some light showers in the Central Valley we'll see in the radar. But this is another really beautiful little disturbance off the coast of Oregon. It's kind of spinning around madly. It's not very intense, of course, but it has to have a connection to an upper level feature, and we'll try and draw the connections for both of these features along the coast. But they have, fairly expansive circulations in terms of their area, but they're not very intense. But they do present themselves nicely on the satellite The more impressive looking circulation is this one here. It's maybe a little bit east of the date line, or west of the date line, sorry. And that's a pretty impressive looking structure, but one, it can be misled by the sort of oblique angle. It's not easy to tell exactly how well structured this thing is, except the cloud head looks pretty solid in this whole region south of the Aleutians. And then much lower stratiform looking clouds, probably convective in the open cellular sense back here. So this is pretty cold air, probably -30 or colder. Fun experiment here is to try and guess the temperature at 500 millibars based on the spacing of these cells. When they're not organized like that, that can be even more fun because the guess can be more accurate. I don't know if the organization kind of puts the kibosh on whether or not the spacing really testifies to the stability or not. So I would, with less confidence, say probably about -32 or something off the coast at 500 millibars. Okay, let's, well, why don't we just go to radar first, Pete? Let's go to radar. We've seen a lot of cloud elements around the country and on the coasts. Let's see which fraction of them are precipitating. And this is higher resolution. Pete solved a problem for us where we were getting stymied. We were getting the Heisman on these mosaics earlier this week, but Pete came to the rescue as he always does, and we've got it solved in a day, or something like that, within the day. So a little bit of lake effect perhaps in the Syracuse area. That's it for the eastern third of the United States, which is just incredible. But we saw that in the satellite, warmed up so fast in the southeast, no clouds. A little bit of light precipitation. See, Pete, this is what I thought reflected the higher resolution. It just looked different today, cobwebby, and but a little bit better resolution of the light showers that are falling in the plains of Colorado and western Kansas and the panhandles of Texas and Oklahoma. Here is the little curved piece of the cloud head with precipitation falling out of it, moving across the coast from San Diego into interior Southern California. Maybe there's just no radar right there. It's kind of disappearing. I don't think it disappeared in the satellite. And then you can see just a whiff of some of the cloudiness that is, or the precipitation associated with the cloudiness off the Oregon coast. Remember, that cyclone was just kissing the coast with its clouds, and this is a little bit of shower activity that seems to go with it. And here's the showers that seems independent from the southern system and from the northern one in the interior valley of California. And a little bit of light precipitation across southern Manitoba into Minnesota. So I'd like to see what the structure at upper levels is associated with these two disturbances. So let's go next to 500 millibar now. And for those who have never been to the discussion before, it's not a formal presentation, so it's not a lecture. If you've got a question or you want to make a comment about something, please feel free to do so. That's the whole point of this. And also with these masks on, it gives me a chance to catch my breath. So I also appreciate it for more than one reason.
This is 0Z. Actually, hang on, we can fix that.
Pete can fix everything. You just
Not
watch.
everything. There was a missing frame, so I redid it, but that updates the current frame, and I forgot, I got involved and forgot to do that, so we can look at it from the loop. This is the current.
Okay, so this is the 12Z
Yep.
from this morning. Thanks, Pete. So remember we had a train of storms heading up into the Labrador Sea. The leading one was associated with this perturbation in the flow, nicely curved flow right there on the southwest coast of Greenland. The second one didn't look quite as well organized as that, and that's probably associated with this curvature just south of Newfoundland. Very cold air in the middle of this upper trough. So this isotherm right here is the -35-degree isotherm. So we've got as cold as -46 in the observations at 500 on March 4th. Oh yeah, March 4th is the only calendar day that doubles as a sentence in the English language. Think about that. And it used to be Inauguration Day, which is a good idea. In fact, in 1909, wasn't it? Taft's inauguration was snowed out after the forecast was for beautiful weather. Heads rolled at the Weather Bureau at the time. Taft enjoyed one term. And that was the end of that. So, here's a strong baroclitic zone aloft from southern Ontario, or northeastern Ontario, down to about where we are here in Madison. We're on the warm edge of it. It's about -20-ish just to our north and east. And it's, as I said, -35 by the time you almost get out of Ontario. So there's a really strong temperature contrast there. A little bit of confluence in the flow as well. And we saw some interesting clouds this morning. Some of them had gravity wave structures in them, and maybe that's tied to the approach of this just little bit of a trough feature in the west-northwesterly flow, but it's cold, the northwest-northwesterly flow. And then on the west coast, interestingly, there's our disturbance off the coast of Oregon. -34.2 is what the analysis suggests. The OBS have minus 29 at Quileute, minus 27 south of Portland, so something in the minus 30 range, but they go way down to minus 34 in the analysis. So that's interesting. Pretty sharp curvature feature. I think at the prior time, Pete, can we go to the prior map since we're in the movie? Look at how much development occurs there. There's not much of there's a curvature feature there, but it's not really put together well, and it's got this weird high amplitude ridge out ahead of it. Just 12 hours later, that's nicely cut off. So that's a nice looking feature. This is the one over the Bight of California where, given its latitude, it's still anomalously cold, I imagine, but not as cold. It's minus 25 at San Diego at 500 millibars. I know that at LA, March is their coldest month of the year at 850 millibars. I wouldn't be surprised if the same is true for San Diego and at levels above 850. And this might be one of the examples of that. So let's, just for the fun of it, what did this look like 12 hours prior? Same structure, just kind of moved inland. Okay, and that's more like what it looked like on the satellite. Okay, so that's what we've got at 500 millibars.
Craig was going to say something.
Oh, yeah, go ahead.
I just want to point out those cutoffs in the west are very typical beginning around March.
Yeah.
And what they do is they raise hell with predictability in the mountains. Because the mountain predictability for precipitation and weather is all determined by upslope. And the upslope reverses back and forth with those little waves
Oh,
going
yeah, I
by
guess
because
that's
of the cutoffs.
Yeah.
In the winter, more in the dead of the winter, it's more straight westerly. Almost, typically, you can have this, but it's not as often.
Yeah.
This time of year, so when we went up to Steamboat and we were trying to forecast snowstorms while we were up on the peak of the ski area, we would have a heck of a time with these little cutoffs.
Yeah.
And the models would work great right up until about March, and then all of a sudden.
That is interesting. I didn't know that, but I did know about this weird climatological thing about LA being the coldest month of the year is March, and 850. And so here you got a connection between a climatological maximum in such features must be the case, otherwise you wouldn't have your coldest 850 temperature at LA in that month, and then predictability issues. How interesting. Yeah, they seem disconnected at first, but of course they're not. That's really interesting. In the old days too, I remember, this might be another feature, is the cutoffs that make it to the southwest, the Four Corners area. When do they, quote, eject into the floor? Remember that discussion? It was always a tricky forecast. It's not so tricky as it was, but maybe it still has a residual of that difficulty. That's interesting. Let's see what it looks like at 300 millibars, people. Okay, so at 300 millibars, we've got little jetlets associated with both of those disturbances. This is the one off the Oregon coast, and here's the more intense jet associated with the feature at 300 millibars off the Bight of California. So that's quite interesting. We have to go higher and see whether or not that's got a subtropical component. And here's the perhaps main polar jet, at least on the western side of it, coming across the Great Lakes, and we're on the anticyclonic shear side and the entrance region. So let's see, that's going to be the ascent region. We see some cloudiness in the sky, maybe later today as the jet goes by. But of course, what really matters is how fast the flow decelerates or accelerates in the entrance region. And if it's spread out, if it's kind of a stubby jet entrance region, you get a lot of vertical motion. If it's kind of an elongated one like this, maybe it's middling at best. And we're downstream of the ridge axis as well. So you have to add these two things together. The transverse circulation, which might promote ascent in this location, is countered by descent from the upstream negative curvature maxima. So maybe we get a wash there. Okay, let's go to 200, Pete, if we could. I'm interested to see what sort of structure there is at 200 millibars in both of those features off the coast. Yes. I'm very happy about this. Greg's probably not. Polar jet is driving the show over there, all the way down to the latitude of northern Mexico. Okay, there's just no question about that now. And it's definitely a polar jet up in the Oregon situation as well. And that's the way it should be. We all know that. I'm kidding about that. But you can see substantial evidence of high wind speeds in both locations over the Great Lakes and the southerly flow off the coast. Makes it a little bit hotter at this quick and dirty way of determining whether or not the core of the jet is polar or subtropical.
That is a subtropical jet down there in the southern part. That-
Right, right.
yeah, and it's
The
built.
wind speed maximum,
Well, the one,
is-
the one that seems to be coming more from the north, that piece there.
the wind speed maximum is reached at 300 miles, not 200. So if it's a cigar, the center of the cigar is at 300 miles.
Well, whatever. I mean,
Don't get too
that's your
scientific on it.
definition, you know, I think it's a little lame. Because I think really you define a subtropical jet as one that's bounding a boundary between tropical air and air further north. And so it really, I think the real measure of a subtropical jet is the low potential vorticity on its equatorward side. Now, this is not very strong yet, but I think I texted you earlier. This is building over the next week, and we're gonna have a subtropical jet coming into Baja over the next week. We haven't seen for a little while.
Okay, that may well be true. I can't testify to that here, though.
And I think it's because there's some stronger convection in the Pacific, which has been somewhat
Revving it
absent
up.
this year, probably because of La Nina
Yeah.
in the eastern Pacific.
That's sensible. I mean, you can rev it up that way. Any way you can build the PV gradient on the right isotopes, you get the wind speed maximum. So we have an objective scheme that kind of tries to put both the PV gradient and the isotropic level into play to figure out the jet. I don't have a quick access to that right now, and I didn't look at it today, but that's another way that you can make this determination. I bet it's going to look like what I'm thinking, but I'd be very interested if it weren't, because that makes it an interesting problem. Okay. Also, for those of you who are visiting, we have this kind of argument every week, and we enjoy it. You know, Greg was just telling me, he says, you know, he moved to another office, and he said, I just love coming into your office and arguing with you. And he hasn't stopped doing it, even though he has a little bit longer of a walk, so. That's what's one of the great things about working here. To be quite honest, I got an opportunity to use this as an example. This is exactly how, we've been friends for 30 years. We didn't know each other beforehand, and we do nothing but argue and cheer on the badges. So that's it, and we have a great time doing it. Okay, let's go to 700 millibars, the often neglected 700 millibar level. I just want to see what the kind of middle tropospheric baroclinicity looks like for this storm as best we can, for the two storms on the coast. So we're at about minus 10-ish, minus 18, sorry, that's the cold pool at 700 millibars right off the coast with the disturbance off the Oregon coast. And not quite as cold, of course, we saw that at 500 millibars too on the feature further to the south. And this is a local curvature maxima. This one's embedded in a much longer, a larger scale curvature maxima. And I think it's this feature right here that ends up playing a role in organizing the weather over the plains during the day today and into tomorrow. So that's going to be our substantial weather producer. We noted some of the vertical shear in the satellite picture, evident in the satellite picture, and you can sure see the horizontal temperature contrast associated with the cold front of storm number 2 that's made its way toward Greenland. Storm number 1 is up here. It's got no longer any obvious thermal structure, even at 700 millibars. But the cold front, perhaps that used to be associated with this structure, is very evident right in this location and all the way down to the New Jersey coast. So that's very nice evidence of what we were saying, just based on the satellite picture.
I'll point something else out. If you look at the region of Colorado, New Mexico,
Yeah.
and Kansas, you see that very wavy, noisy-looking
Yeah,
contour.
right.
And that's because of the loss of inertial stability. The fact that as inertial stability goes down, the ability for the atmosphere to maintain geostrophic balance weakens, and you start breaking up some of the balance flow into gravity waves and balance flow. Balance can only exist on larger scales, so the smaller scales become more gravity wave-like, and that's usually coincident with a lot of convection as well. And so that's really what's happening there. You'll see that a lot in the mountains when you have low inertial stability, perhaps affected in from the tropics going on.
Yeah, because this, if you did back trajectories on air in this region at this level, it undoubtedly is coming from the subtropical eastern Pacific.
Right.
Yeah. So, and then, as you pointed out earlier, low PV on the anticyclonic shear side of the jet. So, and then this is the place, Pete, where I really noticed the higher resolution. You saw a little bit more character to this kind of spider web looking precipitation in the radar. So that'll be nice to see these things kind of erupt a little bit more easily with that high resolution.
And I've noticed it tends to look a little fuzzier especially with the real low reflectivities, there's a lot.
Yeah.
You see the wind farms really well too.
Oh, I
Overnight.
didn't even know that.
They're
That's
everywhere.
gonna be interesting to see.
You know, you could point out that that's really the difference between the tropics and the extratropics. In the tropics, you have the low inertial stability, and so balance is difficult to maintain, and so most everything is smoothed out over time. And that's what's happening here. The gradients are being smoothed out. They're breaking up into gravity waves, and it, you know, it's behaving a little bit like tropical in that region. It's a transition that's occurring because of the low stability tropical air that's being impacted in it.
Yeah. That's interesting, and we'll see whether we see such a signal when we move into the forecast as this upper feature moves across the mountain. Part of that, I think disruption is also a function of the presence of the mountains, but these are two separate but similarly contributing factors to interesting things that happen in the lead over the Rockies itself. One last one, Pete, 850, which we probably won't see much at all on the west because we're too low, but we'll see something about what's going on off the Atlantic coast. And then we'll move on to, I think, a forecast. Get everybody out of here. Okay, so here's, look at this temperature contrast at 850. Very easy to find the cold frontal edge on this one. It's not this plus 10, it's this plus 5, I think, for me. And it comes right up into the center of the storm. That's a beautiful. If I'm drawing this with a pencil, why don't I just make this tighter? If I have no reason not to, I'm going to do that. That's just my art. Here's a strong local warm advection. Look at that. A jet at 850 cutting across the isotopes. Quite strong forcing for convergence of the long isotrope Q vector right in this location. That's going to be a region of ascent. It may just be moisture starved. The dew point depressions are, 18. Oh, these are actual dew points, aren't they? Yeah, I think they are. 12. No, they're dew point depressions. So this is really dry air. It's going to take a long time for that to get up there and turn into clouds. But that's the place where it might likely begin to do that. And you can see the closer you get to the ground, the more shape there is to the evolving geopotential height or pressure field. There's a feature right over southern Nevada that maybe is directly a consequence of the curvature maximum off the south coast of California. Then there's this feature which kind of lines up in a suspicious way to make one think there's kind of got a lee component to that feature. The isotopes at 850 don't really have the characteristic maximum right in the geopotential height trough that's characteristic of lee-side troughs, but they're not very far off from that. It just wouldn't be a textbook example to me. So I'm not sure what to make of this structure. But it does not really have an obvious connection to an upper level disturbance of note at this early stage. But I have a feeling that when this feature off the coast of California moves this way, it's going to organize this whole complex into something a little bit more structured. And there's plenty of baroclinicity to organize. Here's a low-level baroclinic zone. That's actually the westward extension of the cold frontal baroclinic zone from Greenland, and then some baroclinicity associated with the upper cold cutoff that's off the California coast. So there's plenty to put together there, and it's going to begin to be put together. Well, it is right now, and it's going to continue through the day today and into the night. And notice how warm this air is. We're in the mid-teens at 850. So what do you add? About 6 degrees, 9 degrees? So something like 23. We should be 60-something tomorrow at some point during the day when we bust into this really warm air. If we do, depends on where exactly the cyclone develops and how strong the southerly flow is. But it's not out of the question. So we'll see what happens in our forecast as we move forward. Those are the basic ingredients. So before we go to the forecast, any questions or comments?
I'll throw a comment out there.
Yeah.
Throw it back to previous Weather Watch interjection. When I talked about the drought conditions in the Southwest and
Yeah.
the lapse rate impact, that's what we're actually seeing for the severe weather in Iowa tomorrow is that trough that we see over the Four Corners region right now is basically going to be transporting about 9, actually exactly dry adiabatic lapse rates from that 700 to 500 region, and they're modified as it's transported along the way and weakened. But as you get into the forecast, you'll actually see that those elevated lapse rates are coming directly from that drought region.
Very interesting.
And the intense temperatures and probably capping lack of convection preceding it is what's allowing it to make it relatively unmodified up here, and then for the subsequent severe weather afterwards. So the
Very
drought conditions in the Western Plains right now are actually a pretty big part of what's causing this evolution to happen the way it is.
That's really interesting. Thanks for that comment. So it's like an elevated mixed layer, but it's not really starting quite as elevated as the traditional one. And as it rides up, the inversion on the bottom gets weaker and weaker and weaker, and so it's easier to blow through it. Oh, that's really interesting. Okay, so now we're going to head into territory, forecast territory, talking about features that I don't know that much about in severe weather. So please help with any additional comments along similar
What
lines.
do you want to use for
GFS, I guess.
ours?
Yeah.
Or pivotal?
No, use ours. And let's start at 500 millivolts, please. So here's our 500 millivolt map. The shading represents the absolute vorticity.
Might want to just illustrate where you are on there. It's might be hard to see the back.
Yeah, I'll do that too. And the white lines are geopotential heights, and you might be able to see wind vectors. Those are the full wind, not the geostrophic wind. And then here's Washington and Oregon. So there's our feature off the Washington-Oregon coast. Here's the feature that's made its way inland, and we saw that on the satellite movie. This is Dallas right now, over Southern California. And then the kind of little bit of a negatively tilted ridge that's just to our west, and features to the east. So we're going to concentrate on this region of the country as that forebodes for our weather. So we've got, this is the upper trough probably of most significance, but I haven't looked at the forecast. I'm not sure of it. This is the one that looks the best. And so we'll see how they come together. Let's go 6 more hours into the forecast here, Pete. So this will get us to tonight at 6 p.m. This feature is getting a little bit stretched out, but there's still a vorticity maxima over southeastern Arizona. And I'm looking more at the geopotential height lines. This trough is just broadening a little bit. It's still got a very intense wind speed maxima on its southern edge, and then suddenly difluence, and some of the squiggles that Greg was talking about perhaps showing up in the forecast because they don't exist in many other places. And so, and also pockmarked places where the vorticity is negative, absolute vorticity is negative. That's a sure sign of convective activity. And downstream of this wind speed max and curvature max, right over southern Colorado, northern New Mexico, looks like a region for some anticipated development at the surface. And here's the feature off the Oregon coast, which has kind of crashed into the Eureka County in Northern California. And it's also got a very sharp wind speed maxima on its southwest side, and then broad difluence over Nevada. So potential for some substantial development over Northern California. Let's take a peek at the same time at the sea level pressure forecast, just to see if we still have 2 separate features in that part of the world. Here is the one over Colorado. That seems to be the beneficiary of the difluent flow downstream of the curvature of the southern upper trough. Then we remember Northern California was our location for the secondary one. Here's the signature in this thickness field, low upper level heights. And there is a tendency for a little bit lower pressure there on the California-Nevada border, but it's not really as potent looking a system as this one, although it's not out of play. This is a development scenario, so is this. And you can see the 1,500 thickness in yellow kind of ridging up ahead of the minimum in sea level pressure, and that's indicative to the slightly to the east of pretty strong warm advection. First, uniform warm advection, which tends to come with little or no vertical motion, then differential warm advection, which starts to be frontogenetically active. Okay, let's keep going at 500 feet. Let's go 6 hours further than we were. And then of the 2 features, this one certainly looks the most impressive. This one's the most proximate. It's now, to help you see, the geopotential height lines are still strongly curved over central New Mexico, and the local wind speed maxima is right in this location. So it's downstream now, maybe over western Kansas and southwestern Nebraska, that we might expect the most intense development. And over in this one, we're going to have development over northern Nevada still. Although maybe this thing is getting itself cut off so substantially that the development gets cut off a little bit as well. So let's now go to the surface again. Thanks for bouncing around here, Pete. There's our storm in central Nevada. It's now down about 1,004. Hard sometimes to really put a structure to these things over the mountainous state of Nevada, especially. If you ever look at it, it's like an accordion, you know, topographic map. This thing's emerging out into the plains on the western Kansas and eastern Colorado plains. It's down to 998 millibars. That's, I think, a drop by 2 millibars. The thickness ridge is out ahead. Here's precipitation where the temperature advection starts to be differential, and it's not really happening here. But the fetch of air that's feeding into this eastern side of the storm is coming off the Gulf of Mexico, not particularly strongly yet, but it accelerates with the low-level strong winds across the plains. Let's keep on going in this sequence, because this is going to be an interesting weekend for us. So this is now valid tomorrow morning at 7 a.m. at 500 millibars. And there's our western storm, still making slow southward progress. It's now made it to the latitude almost of Las Vegas and a little bit to its west. Here's our upper level trough. It's a cutoff, not a cutoff, I'm sorry. It's a local curvature maximum right in this region in the extreme western Kansas. And it maintains this intense wind speed maximum at 500 millibars. So we have downstream of the curvature maxima and jet exit region cold side ascent over Nebraska. I'm going to guess that that's where our cyclone looks most intense at this time. Over here, it's going to be right over the three-state area, northwest New Mexico, Arizona, Utah, and parts of Nevada. So let's go to the surface at the same time, Pete. Yeah, so our cyclone over here is maybe a little bit further west than I would have anticipated, and it's about the same intensity. And then here we are over sort of southern Nebraska, northern Kansas, 997, a little bit more development and a little more consolidation of the baroclinic zone to the north. And now the precipitation is starting to break out over parts of our own state and certainly over central Iowa. I don't know what the situation here is for severe at this time. Probably too early in the day, but maybe it evolves during the day tomorrow. Okay, let's go one more time, Pete. At least one more. We'll go to 500 first. So now we got this deep curvature maximum with two separate features. Here's our more proximate one. It still looks pretty well organized, and I'd guess the development max is going on right about over Sioux Falls. And then here's our upper wave with development probably in southwestern Utah, maximized there. I like the fact that the wavelength between the trough and the ridge has really shrunk over this period of time, and that means that the flow has to curve a lot more, and so there'll be a lot more upper divergence over Iowa by this time, which is now noontime tomorrow. So let's see what the surface forecast suggests at this time. (995), so it's barely developing, but it is developing. This feature here is not. The sea level pressure has gone up a little bit, but it's gotten a little bit better organized, it looks like to me. It's over central Utah. So there's a double-barreled minimum in sea level pressure. This one, of course, bearing down more obviously on us. This thickness line right here is 558. So that's a lot of strong warm advection has been building to get 558 almost to the Illinois border. I think you take the leading 5 off, and that's a good estimate for your high temperature tomorrow. Probably a little bit of an underestimate. So I don't think 60 is out of the realm possible at all. It's quite probable, actually. Very strong warm advection. But that probably will be the cap, because you have to go quite a bit farther south to get substantially warmer than that. Let's, for a fun of it, Pete, let's go to 850 at this time. So, whoa, look at this. We haven't been in green at 850 in I don't know how long. But here's our cyclone developing right along the border of Nebraska, Iowa, and South Dakota. Very cold air, of course, on the back side of it. Flood of warm air. But this is about the limit of the warm air into this kind of olive color, which is about +8 at 850. So add about 9 to that 17. Yeah, you're talking close to 60 or over 60 degrees if that's going to hold out. There'll be clouds that'll take some of the sun away, but I think advection beats radiation tomorrow anyway. So I wouldn't guess anything lower than 60 for tomorrow. And the frontal activity is further to our north, so maybe more substantial precipitation develops later on further to the north. Anything about these series of maps for severe weather experts that stands out? Kelvin?
It probably get a little lower scale or higher scale resolution, but I mean the main things that jump out are just a strong negatively tilted trough, lots of upper divergence, and the focus on the development of the surface load kind of becoming vertically stacked. It's the focus is very much in the cold core region of the cyclone, given the unseasonability of the moisture and the temperature advection. It's not quite enough for a classic severe weather outbreak, so you're really relying on those cold temperatures a lot to destabilize the profile. That's why most of it's confined to the to pretty much the Iowa region is some of those synoptic features that you identified. But I think the moisture return is only supposed to get up into the upper 50s dew points, which is climatologically speaking the bare minimum that you can expect anything to be producible. And you're mainly going to be dealing with hail production, though, given the cold temperatures aloft for any convection. But given the curvature of the flow and some of the mass response, you'll see that there are large photographs that can result in rotating updrafts and thunderstorms, but the primary focus will be on hail due to the upper features.
Okay.
Can I make a comment as well? I was looking at the inertial stability and the outflow layers, and it's not conducive to convection up in the upper Midwest or any place where, I don't know, SBC is putting out kind of an outlook for something significant up in the upper Midwest, just for our west. I don't see that, but that's what they're saying. It just doesn't look to me like the inertial stability is strong enough that it's going to keep it fairly geostrophic and probably be kind of oppressive to convection trying to blossom in that kind of flow.
Yeah, the bulk shear profiles, we might see like a broken line under this.
Okay.
But I don't, it's kind of marginal.
Okay.
But-
Well, thanks, that's interesting. I don't know any of that stuff, so that's really quite interesting. It's gonna be warm, you'll hear a rumble, and it's likely to be wet a little bit tomorrow. Ian?
Yeah, I just have a question about the inhomogeneity and the warm air advection. In the region where there is all uniform warm air advection, you would still imagine that your isotopes extend northward and upward. So I guess the question is, if there's uniform temperature advection everywhere, does that tell me that the isotopes are actually moving northward and no flow is going anywhere in the vertical? Whereas if there's inhomogeneities, then the flow is actually moving up the isotropic surface.
I don't think of it that way. I'm not prepared to say no or yes. I don't think of it that way. I think of isentropic flow relative to isotopes is not a dynamical explanation for vertical motion. It is a topographic explanation for vertical motion. Whereas if you have differential temperature advection, you are changing the nature of the vertical shear. And the geostrophic balance, when perturbed like that, has a response that takes the form of thermally direct circulation, so that you have a dynamical response to the alteration you've made by the differential temperature advection. I'm not ready to say that your idea that just moving all of the whole bundle of isotopes ahead at the same speed means that that the air doesn't flow up them. But I can say that that's not a secondary circulation. If you get ascent there, you're not getting it from a secondary circulation. That's a response to a geostrophic adjustment process. But it's a good question. Greg?
I think you can diagnose whether flow will move upward along the isotropic surfaces by looking at the upcoming stream function on an isotropic surface and see if there's a gradient of that that would drive the flow upward. But I agree. I look at it the way Ian does, and I think there's a combination of both things and how you separate whether it's the movement of the isotopes or the flow upward is not straightforward.
Yeah.
I think you'd have to look at these things like Montgomery stream functional gradients.
Yeah, and you have to know something about the system motion and all that to take it out, to feel like you can say what's moving relative to what's going. In the secondary circulation-based arguments, you don't have to worry about that. And that, to me, that gives them more appeal, although I agree completely that that's not the only thing that's going on in the atmosphere. It's just a little bit easier to make sense of that one.
The movement of the
given these kinds of
isotropic
matters.
surface in that way is kind of related to gravity wave propagation. And because the isotropic surface is anchored where it is by gravity, and for it to move, you're actually lifting the atmosphere and sinking it on either side. So that's actually equivalent to the propagation of the gravity wave if you look at the shallow water model.
If you discount radiation, because the bottom boundary for the isotropic surface is also capable of moving if radiation intervenes.
Yeah.
You can make it warmer at a spot and force it forward.
Right.
Yeah. So, but that's also true when you think about the adjustment. You're not thinking about diabatic effects in that case either. Okay, so I think, let's go ahead, let's stay at 850, Pete, and just go ahead maybe every 6 hours. Now we've seen sort of how this thing's evolved. Let's just see what sort of shape it takes by the time we move through the day tomorrow and into the early part of Sunday. So this is now midnight tomorrow night. Cyclone's most intense at 850, presumably also near the surface somewhere in southern Minnesota. We're still obviously on the warm side and still the beneficiary of at least weak warm advection, certainly no cold advection. The cold advection is back here over Nebraska and Kansas, and it's gangbusters. There's really strong subsidence probably being imposed in these regions at this point. And there's pretty decent differential temperature advection all the way along and north of the Upper Peninsula into Lake Superior, whose northern boundary has disappeared on this map somehow. So, yeah, it's weird. But anyway, there's your baroclinic zone. Frontogenetically active, I'm guessing, right to about the Arrowhead and then to the east, but not probably to the south until you get over the Mississippi and western Iowa. Let's keep going, see what happens with this
Here
thing.
too. Keep your eyes on that.
Yeah, no kidding, that's for sure.
42.
So by this is, that was 7 p.m. Saturday, sorry. This is midnight tomorrow, and we're still warm. This might be the time when the weather gets particularly interesting with a cold front at 850 to our west, but at the surface probably coming right through. So somewhere probably between 7 and midnight tomorrow is when we might hear our rumble, more than one rumble, as it comes through. I really like how this warm front's taking shape, and it's pretty intense and it's strongly frontogenetic. Can we get a peek just at the surface for the precip forecast at this time? Yeah, some pretty heavy precipitation embedded within this warm frontal region, right over the state of Michigan, northern part of the state of Michigan. Maybe that's where, for some reason, the model's got convection going off. It looks like it's superimposed upon a band that cuts across like this along the warm front, so I don't really get that one, why that's there. Okay, 1,000 and about maybe 998, 996 millibars over La Crosse by this time. And let's go maybe 12 hours ahead this time, Pete, at 850. So our storm goes by us. By the time we get to midday Sunday, we are then in some substantial cold advection. Not brutally cold by any stretch, but cold. It'll feel miserable after tomorrow, but it'll be a little bit colder. And we're not done, so let's just kind of click through these rather quickly. Maybe we can even run the animation because we have an interesting event taking shape for next Friday. So let's stop it at the time we were sort of just at, and then we'll step through. Thanks, Pete. So here we were just about at midday Sunday, so here comes the cold advection. We can keep clicking forward. These are every 3 hours. So it funnels in. There's a nice cold front back, at the front edge of it. It's pretty nice. But we're just dead in the cold air, not really much cold advection, just not getting any warmer. Here comes a disturbance in the northwesterly flow. It even builds a little thermal ridge, like an Alberta Clipper type disturbance. Brings us a little bit of warmth. What are we on Wednesday? So that's a little bit of cloud, maybe a flurry that comes in. The next push of really cold air seems headed straight southward, but then it takes a bend. This is now Thursday morning, but watch out for this. This is another disturbance that kind of forms in the lee of the Rockies with a much colder air mass just forward of us, and we're kind of firmly in the colder side of that. That is, I think, -4 to -6. And then an inverted trough develops in the leading finger of the cold air that comes southward along the Rocky, as the cold air funnels southward along the Rockies. And keep on going, Pete. This gets us to midday Thursday. Cyclone, I only saw the 60s, so maybe it's changing. But here's an elongated cyclone. We're still cold and in warm advection. And what about Friday? So one more. This is Friday 12Z. Cyclone's taking a little bit better shape. I suppose most of the ascent is off to the east, so we won't see a lot of precipitation out of this storm, but it begins to be a nice development. Keep on going. That takes really nice shape, very cold behind it for the first afternoon of spring break, or almost the first afternoon of spring break. Very chilly. I wouldn't be surprised if it's snowing on the northwest side here a little bit. So it will feel like a return to winter if this forecast verifies about this time next week. How long-lived it is really depends on what happens with this perturbation in the flow. I don't suspect it comes straight southward, but this little slug, all it's going to do is get modified as it moves southward. And the modification rate will determine how miserable it is the first weekend of spring break around here. It's going to be windy and cold Friday afternoon as well. So a big change. This weekend's going to be especially the first half of it, really unusually warm. It's gonna strike you as unusually warm, and then there'll be a little bit of thunder on Saturday night. Sunday, a cool down, maybe stays cloudy most of the day, and then a little disturbance Tuesday to Wednesday, and then a more substantial one on Friday. So we won't really feel like we're in spring this week. We have maybe for parts of the prior 2 weeks, but not this one. So that's really cold, coming right in over us through the early part of that weekend. So that's what it looks like right now. We'll have a discussion next Friday, but it'll probably be somewhat abbreviated as people are maybe on their way out of town and so on. And if you're trying to keep record of perfect attendance, sorry if you have to leave town and miss it, but we'll talk about the weather next Friday. So thanks for all the contributions, especially about the severe weather, and I'll see you all next week. Pete, thanks so much for running the show.
We need to look at the suite of models.
I know, and even this is different from the 60, which I brought to class. It's a lot more.